Welcome everybody to this week's GBO Community Zoom. I'm Jim Jackson, the director. Just a quick update on things going on at Green Bank. Proposals from last semester are being vetted and will be reviewed, so stay tuned for the outcome of those. Observatory is running well. One good piece of news is that the COVID restrictions of pre-Omicron have been well, how do I put this? The Omicron restrictions have been superseded by our pre-Omicron policies. And the good news is that we can, at the observatory, staff can again travel, but more importantly, we can accept visitors. So if you're interested in coming to Green Bank, we are now open for business. People are back in the Jansky lab working, and it'll be great to have some of those restrictions lifted. So that's all I have. I'm the speaker today, but Jay wanted to mention a few things about some statistics about Community Zoom, so I'll pass it off to Jay.
Okay, thanks, Jim. We started these community Zooms in the summer of 2020 in order to keep the scientific community in touch with events at the GBO. And since the first one, we've had more than 40 talks by scientists on all sorts of diverse topics. Just interesting to hear some of the statistics just from the last year, which is that we've had more than 600 individuals attending at least once, representing 33 countries from Argentina to Zambia. And I think if you look at the talks that are coming up in the next few weeks, you'll see really the diversity of GBT science. I want to emphasize that all of these talks present GBT science. And coming up in the next few weeks, we have talks on planetary radar, blazar jets, searching for intelligent life, and monitoring the solar wind. And so today's speaker is our own Jim Jackson from the Green Bank Observatory, and he's going to be speaking to us about RAMPS, the Radio Ammonia Mid-Plane Survey. Let me remind everyone to submit questions through the Q&A button on your lower right of your screen. Take it away, Jim.
Great, well, thank you. So I'm here to talk about the RAMPS project. This is a large ammonia survey project that we did with the Green Bank Telescope. I'm just the presenter here. Taylor Hogg, my graduate student at Boston University, did the bulk of the work, and any mistakes are mine and all the glorious work is his. I'm free to admit and freely admit that the RAMP survey is named after the beautiful wild leeks of West Virginia that are common in the northeast United States. If you've never eaten a RAMP, they're delicious. The RAMPS project has a host of collaborators from kind of all over the world. More are welcome. Here's our list of collaborators. And we'll talk a bit about motivation first. So the question is, why is high mass star formation important? Well, high mass stars really dominate the chemical and energetic input into the interstellar medium. They are the most luminous of stars, and they dominate the energy. As their explosion also adds heavy elements to the interstellar medium. Once the high mass stars form, that energy can disrupt the interstellar medium via H2 regions and supernova feedback. And of course, high mass stars therefore have an enormous influence on the stellar cluster formation and the galactic evolution. The trouble with studying high mass stars is they're much less understood than low mass stars, and the reason for that is they're quite rare, they're more distant, they're harder to resolve, and they're also deeply embedded in dense molecular clumps, and that requires observations at longer wavelengths to penetrate this obscuring gas and dust. We do have kind of a broad understanding of how the high mass stars form. The unit that I'm going to emphasize is the clump. A molecular clump is a few hundred to a few thousand solar masses, a radius of about a parsec. Within those molecular clumps, molecular cores form. And those cores are of order solar mass or more, 20 to 30 solar masses for a high mass star forming region. These are the entities that form individual stars or binary systems. And they're about 0.05 parsecs across. A high mass star begins its life in a quiescent state, which is cold and dark, presumably collapsing. Then a protostar will form in the middle. These protostars can launch bipolar outflows. Once nuclear fusion begins, the luminosity increases dramatically. It begins to ionize the material and influence the material through winds as well. As these H2 regions expand, they disrupt their surrounding clumps with a main sequence lifetime of a few million years. So that's the basic theoretical picture. After the star exhausts its fuel, it will form a supernova, explode as a supernova, and here's a nice image of a supernova, and that supernova could also interact with some nearby clumps or with its parent clump, and that is a topic that is not well understood at all. So these stars can feed back into their parental material through several phases of stellar evolution. In the protostellar or stellar feedback, you can get protostellar outflows, winds, and radiation. And of course, a supernova will also inject mechanical energy into any clump that happens to line its path. I'll talk a little bit about all of these. So there's some open questions in high mass star formation. What are the dynamic states of the youngest clumps? Are they supported by turbulence, or are they collapsing? Does protostellar stellar feedback regulate the evolution of clumps? And in order to understand, we have to understand how feedback actually changes these clump properties. So how does the temperature, for instance, or the turbulent line width of the clumps evolve? And can feedback from supernova influence the evolution of clumps? Supernova may be able to inject heat and turbulence into dense gas. If that happens, does this interaction trigger or inhibit star formation? So these were the questions we were trying to address, and Taylor Hogg did some amazing work pulling all this together, and so I'm going to present some of the work from his thesis. So we decided that ammonia is a really ideal probe for the high mass star forming clumps. The inversion lines of ammonia are all roughly the same frequency, and yet they span a wide range of temperatures, so you can probe different physical regimes of the gas. They probe high density material. That's perfect for high mass star forming clumps. And ammonia also has the interesting properties that you can compare the amplitude ratios of the various inversion transitions at different energies, and that's very sensitive to temperature. You can also compare the main line to the satellite lines. These are nuclear quadrupole satellite lines, and that can help establish the column density. So with a minimum of observational effort, you can get things like the turbulence, the velocity field, the temperature, and the column density structure of these clouds. So we conducted the radio ammonia midplane survey, or RAMPS, with the Green Bank telescope. Our main tracers were the ammonia 1,1 through 5,5 inversion lines. Resolution is about 32 arc seconds. We've done about 21 square degrees. Took us about 500 hours, and we collected data for 5 years, from 2014 to 2019. For a nice summary of our techniques and analysis, see Taylor's paper in the AppJSUP 2018. There is the survey in all its glory. The gray bits are regions we didn't observe, but all the white bits are regions we did. We actually found it more efficient to do these large maps than to concentrate on pointed observations of individual targets, because the turnaround time was so significant in overhead. That was great. So we did a blind survey essentially of all these regions of the galactic plane. We chose the regions that were kind of busy in the dust continuum imaging surveys of the galactic plane that had a lot of material in it. But every clump you see there is real. Every black bit is an honest to God ammonia detection. So you can see that the galaxy is filled with these star forming clumps. We identified 2,680 of them, and all these clumps, because we observed them with all these ammonia transitions, are well characterized. So take a look at this little guy here. This is a clump that we have as advertised maps of gas temperature, maps of column density, maps of the velocity dispersion, and maps of the velocity field. So armed with all this data on all these clumps, we can now begin to examine some of the statistical properties of clumps and try to understand how star formation influences the clumps as they evolve. To establish the evolutionary state of a clump, we use the mid-infrared Spitzer data using the GLIMPS and MIPSCAL surveys. We characterize a quiescent clump as something that's mid-infrared dark, no signs of mid-infrared emission, presumably very cold. As the cloud evolves and protostars begin, you begin to see these zones of protostars, or the dust around the protostar heats up. Eventually you get an H2 region that forms, and we've also classified some PDR zones. These are the interface between H2 regions and molecular gas. So there was the statistics. We've identified quite a large number of each of these kinds of clumps, and now we can examine their properties and see how they change as the clump evolves. First thing we did was start with a virial analysis of the clump, and this is to understand the dynamic state of the clump, whether it's gravitationally bound or whether it isn't, whether it is a permanent collapsing structure or a transient one. And to do this, we did a virial analysis where the virial parameter alpha is the virial mass of the clump divided by the mass of the clump. The virial mass is the mass where gravity and turbulence are in equilibrium. We could get these virial parameters from the ammonia data. We need the size and the line width and the distance. And then the mass of the clump we get from dust continuum surveys with Herschel and others. If alpha is less than 1, the cloud is collapsing. If alpha is greater than 2, it is unbound. So on this diagram, plotting the virial mass versus the clump mass, we have particular zones where the alpha of 1 to 2 region is where the cloud is essentially in equilibrium. Collapsing is to the lower right of this diagram, high virial parameters and, low virial parameters. And the upper left of this is the unbound portion. All right, so where do our data lie? Here are the quiescent clumps. And we separate low mass from high mass clumps. Low mass clumps are insufficiently massive to form high mass stars, making certain assumptions about initial mass function and star formation efficiency. What we will contend is that about any clump that's about 150, 180 solar masses or more will form a single high mass, at least one high mass star. All right, so you see that the quiescent clumps all lie in the collapsing region, well below the bound region. If you add the protostellar clumps, they lie in this region, again, all in the kind of collapsing or region. H2 regions, you see the virial parameters start to get a bit larger, and that's probably because the H2 region is often pushing back against gravity as the H2 regions expand. And finally, the PDR clumps have a much broader dispersion in these, and many of these are unbound. So this is actually good news. We would expect star-forming clumps to be bound and collapsing. One question might arise is, what happens if magnetic fields are providing additional support? Well, we can redraw this diagram under the assumption that magnetic energy is equal to the turbulent energy. That lowers the threshold for boundedness and collapse by about a factor of 2. So the zones are a bit different. But nevertheless, you can see that particularly for the quiescent and the protostellar clumps, the vast majority of the clumps are in the collapsing region. So 80% of our massive quiescent and protostellar clumps have alpha less than 0.5. And so that suggests that most young massive clumps are gravitationally bound, gravitationally unstable. A more direct probe might be to look for dynamic signatures of collapse, and this is a bit subtle. So we're looking at, what we've looked at here is what's called the blue asymmetry parameter. Optically thick lines probe essentially the tau equals region. You can see into a cloud to tau equals 1 and not behind it. Now imagine you have a clump that's hot in the middle and cold on the outside, as you might expect. The tau equals 1 surface, if this cloud is collapsing, the red shifted side here is in the outer parts of the cloud. The tau equals 1 surface is close to the outskirts of the cloud. Whereas the blue shifted side, the first thing you see is, tau equals 1 surface may be in here. So the blue side and the red side are not symmetric and for an optically thick line. And if the gas is dense enough and the excitation temperature is equal to the gas temperature, and you have this temperature gradient, what you will see is the blue side will have a brighter emission than the redshifted side. This will give rise to kind of a skewed line shape. This is a bit of an exaggeration, but we do see in extreme cases line profiles that look like this. I will add that this will also happen if there is a excitation temperature gradient due to a density gradient where the outer parts of the cloud are subthermally excited below the critical density, but the inner parts of the cloud are thermally excited above the critical density. All right, so how do we search for this asymmetry? Well, we can compare the emission from an optically thin tracer to that of an optically thick tracer. And these clouds are so dense that, in fact, and have such high column densities, that in fact 13CO is optically thick. You normally think of 13CO as an optically thin tracer, but the typical optical depth of these clouds in 13CO is 5 or more. So here you see the green lines are optically thick 13CO, and the red lines are the optically thin ammonia transitions that we get from RAMPS. And if we see a velocity difference between these two, what we would expect is the optically thick tracer should be bluer than the optically thin tracer. So there should be a velocity offset between 13CO and ammonia. And in fact, that is exactly what Taylor saw when he did this analysis. If you plot the difference in the velocity of a fitted Gaussian, you find there's a bit of a shift between ammonia and 13CO in the sense that we expect that the optically thick 13CO tracer is going to be bluer than the optically thinner ammonia tracer. And the result is significant. These are three sigma error bars on here. The mean difference in velocity is 0.11 in the mean and 0.09 in the median. So we are seeing this very slight shift, which is indicative of an overall collapse of these clouds. We can break these down into categories. Now our statistics get a little worse here because we have smaller numbers, but we are seeing a significant collapse signature from the quiescent clouds. Again, these are 3 sigma error bars. You can see the numbers here. It looks, this is a significant result. There's some indication that there is a non-zero offset for these other categories, but the error bars are getting uncomfortably large to make any definitive statements. Nevertheless, what we can say is we detected infall motions for at least for the quiescent clump sample and for the overall sample as a whole. One of the questions now that arises is, okay, we talked about feedback. What can we say about feedback? And do we notice changes in the temperature and the velocity dispersion as these clumps evolved? Here's a plot of the values of the ammonia rotational temperature versus the number detected in each of these evolutionary categories. We see quiescent clumps are colder, protostellar clumps a bit warmer, and the H2 region clumps a bit warmer still. So we do see significant changes. Again, this error bar is the error bar on the mean, and there's a significant increase in temperature with these clumps. Same thing happens with velocity dispersion. Here's the velocity dispersion we measure from our ammonia lines, and the velocity dispersion increases as we go to later evolutionary stages in a fairly significant way. So what we can say is there's a significant increase in the clump average temperature and velocity dispersions with the onset of feedback. The final thing I want to talk about is the supernova interaction. And one of the big surprises from RAMPS was the discovery of this particularly weird source. This is the G23 source. Here's a Spitzer image of it, and the contours here are RAMPS ammonia data. The spectrum of this source is extraordinarily unusual, and parsing it took a little bit of effort, but what we've noticed here is we actually have 2 sources along the line of sight. This is on the right, we have an unrelated background source at high velocities, about over 100 kilometers a second. Here's the ammonia emission from this source. You'll notice this weird spike in the ammonia 3.3, more on that later. The other thing to notice is the extraordinarily large line widths of this source. It's over 25 kilometers a second broad. Well, it turns out that our source, indicated here by the star, is coincident with a supernova remnant. Here's the MAGPI's 20 centimeter continuum image of the W41 supernova remnant. Our source sits here on this kind of cap. There are some 08, 17, 12 masers here. And then here's the error circle from the TeV emission, all likely indicating interaction between the supernova and some the surrounding material. When we zoomed in on this object with the VLA to image its ammonia emission, what we found extraordinary surprises. The structure of this thing is just wildly bizarre. So here's the velocity field, and you see that there's an extremely large velocity gradient. It goes from 60 kilometers a second VLSR on the left side of the cloud, and then there's a sudden transition to about 80 kilometers a second on the right side of the cloud. Very sudden, and to my knowledge, this is the largest velocity gradient that we know of in an infrared dark cloud. Taylor also looked at this object with the ALMA compact array, the ACA, and in ammonia, in silicon monoxide. This is a shock tracer, and you can see silicon monoxide all along the cloud too, with a similar velocity gradient, more emphasizing the left side of the cloud rather than the right. Now, let's get back to this weird spike in the ammonia profile. When we looked at ammonia 3.3 with the VLA, we found these 4 point sources with extraordinarily bright temperatures, well beyond thermal. So these ammonia 3.3 lines are scaled by factors of at least 4 to 100. Just put them on the same plot. These have brightness temperatures, we've looked at them in the A array, of over 300,000 degrees. So they're clearly not thermal. These are, and the narrow lines also indicate that these are ammonia masers. Now, it turns out that these ammonia 3.3 masers seem to be associated with shocks, typically with outflows. But in this case, I think something else is going on. Here are the, here are the 4 ammonia masers. Those are the spectra, you know, with the coded by the symbol here. We even find one on the red shifted side. Most of them are on the 3 of them are on the blue shifted side. If you look at the 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6 images of this source. Now remember, as you climb in the JK numbers, quantum numbers, the gas has a higher critical density and is hotter. So the 1, 1 is probing cooler gas, the 2, 2 kind of intermediate, and then you probe very hot gas with the 6, 6, so hundreds of degrees. So what you're seeing is, the right side of the cloud is cold and the left side of the cloud is hot. So not only is there a gradient in the velocity field, indications of a shock, there's indications that one side of the cloud is much hotter than the other side. One way to show this is this diagram. So what Taylor did is looked at the 1, 1, and 2, 2 lines and derived gas temperatures from that. Now remember, the 1, 1, and 2, 2 are more sensitive cold gas. And the color coding there is the density of points that he found in this diagram that plots temperature versus velocity. And what you find is, at high velocities, the right side of the cloud, you get cold temperatures and low velocity dispersions. Now, if you look at the 4, 4, and 5, 5 emission, which is more sensitive to the hotter gas, you get the opposite. The hotter gas is on the left side of the cloud at small velocities, and it also has much larger velocity dispersions. So what I think we're seeing here is absolute direct evidence that the supernova remnant W41 has slammed into this infrared dark cloud, has shocked, accelerated, and heated the left side of the cloud, but the right side of the cloud has yet to be impacted. So we're catching it just as it's happening. I think this is a fascinating source, and hope to look at it further. So the supernova remnant is accelerating, heating, and injecting turbulence into this dense molecular filament. The question of what this does to star formation is an open one. Taylor was concluding that the cloud is probably going to disperse because it can no longer hold itself together under turbulence. The cores is a different question because we couldn't really get good estimates of the viral parameters of the cores. So our conclusions. Most young clumps are collapsing. We see evidence in both the viral parameter and the blue asymmetry. Feedback from the high mass protostars significantly changes the thermal, chemical, and kinematic properties of clumps on spatial scales of 0.3 to 3 parsecs. We see the clouds are getting hotter. We see that their velocity line widths, their turbulent velocities are getting larger. And that supernova shocks can impact and do impact at least one infrared dark cloud. And we see direct evidence of adding heat and turbulence that could possibly inhibit future star formation. So thank you for attention. I'll be happy to take any questions.
Thanks very much, Jim. We've got, let me remind everyone, please use the Q&A button on your lower right to submit questions. But we had a question come in the chat about the connection between the opacity and the observed spectrum in a collapsing cloud. And maybe the thing to do would be to start with you just reviewing that particular item.
Yeah, so of course, if you know, it depends on, of course, the whether or not you have significant gradients in the excitation temperature. So if you have like a super enormously optically thick cloud with an enormous temperature gradient, and you looked at the center of the cloud, you'll see this, you know, blue-red asymmetry, probably a dip in the middle, and the blue side being stronger than the right side. Now look, real clouds are less extreme than our idealized examples. And in these filaments themselves, the motions are somewhat complicated because in addition to collapse motion, you also have what looks like motion along the filaments and some other motions that could easily mask the signal. If you look at the simulations from, say, Vasca Sammadini or Rowan Smith and their collaborators, you can see that Rowan Smith's is actually pretty interesting. If you take the same cloud that is collapsing and look at it from different angles, you'll get different spectral line shapes. So that's why, you know, individual sources are really hard to do with this sort of analysis, and you need the statistical approach. But we are seeing in the statistical measurement that there is a distinct velocity difference between the optically thick tracer 13CO and the optically thin one, Ammonia.
Okay, and here's another question. Is the ammonia data from the Keystone program included, or did you repeat the observations?
We started before Keystone. We did not include their data. Ours was a blind survey, and Keystone zoomed in on some of the, you know, large angular size and nearby star-forming regions in Gould's belt. So it is a different type of survey. They were targeting a few individual star-forming regions, and we were just doing a blind galactic plane survey. The Keystone data are amazing. We haven't done this analysis with their data. We could, and maybe we should, but it is a kind of a complementary project.
And another comment, mass estimates from dust can be largely overestimated. And I think the questioner says because of line of sight emission. Did you consider that in the virial analysis?
Yeah, we did. And look, so we tried to remove the local background. And where our assumption is, you know, the clump is a small scale feature and the local background is a large scale feature. So we did try to account for, you know, unrelated emission along the line of sight. But, you know, the comment is absolutely right. One of the other complications, of course, is if you have a blend of cold dust and warm dust, well, you're going to see the warm dust more than the cold dust, and you can underestimate the mass that way. So, but we did our best job to remove any kind of background and foreground emission that was unrelated to cloud.
It is the question is the implication that gravitational unbound clouds are dispersed and older?
It could be. So, you know, I think that's probably right. So, you know, the clumps that we find in photodissociation regions, for instance, you know, are they pre-existing clumps that just got, you know, caught up in the ride or suddenly exposed to these, you know, these UV fields? They tend to have much larger viral parameters. My suspicion is if you suddenly, heat up a cold clump by factors of 10 to 100, that probably will push it over the edge, and that that clump will probably disperse. But that's what we're seeing.
Okay, we have time for one more question, and we have one. Regarding the virial parameters, I'm curious whether you've considered the corrections discussed in the context of the gas survey by Singh et al. 2021, specifically kinetic energy implied by velocity gradients and line of sight emission. Velocity gradients, not just dispersion.
Yeah, no, and that's a good point. Well, we did not. We wanted to do the simplest analysis first. I don't think that, including the velocity gradients, although, I appreciate the physics of that argument. I'm not sure you're going to increase virial parameters by factors of several, which you would need to make, put these clouds on the bound or unbound side of the line. So I think, we may, if we did that analysis, it would tweak things a bit, but I don't think our general conclusion would be changed.
Okay, let me ask one final question of my own curiosity. Given that a very large fraction of the clumps that you study are collapsing, are you in danger of making too many O stars?
That's a great question. Look, just because the clump is collapsing doesn't mean it all turns into O stars. So an interesting thing is in the competitive accretion kind of model, you have to funnel that gas down into the centers of the cloud, or you don't make any high mass stars at all. And so, it is a prerequisite in that model that you have to have the collapsing clumps. Now, where that material eventually winds up, and the models are silent on, I don't think there's any good model that has come up with a good estimate of star formation efficiency. Maybe someone in the audience can correct me. But I don't think we're in that much danger. Not all that material that's infalling is going to wind up on a high mass star.
Actually, another question has snuck in, and you can probably deal with this pretty quickly. Are the ammonia 33 masers also water masers?
No. Many of these sources have water masers, but they're not the same place. So in order to make a ammonia 33 maser, you have to have a temperature range, a temperature right around 200 Kelvin, and a fairly high density. Water masers are coming from a very different sort of parameter space in the density temperature regime. So I think why ammonia 33 masers are tracing shocks is just due to this kind of narrow constraint of a temperature and somewhat high densities.
Thanks very much, Jim, for an excellent presentation. Let me remind everyone that this presentation has been recorded and you'll be able to view it through the link on the GBO website. We look forward to seeing you all again in 2 weeks on March 16th, when there'll be a presentation by Patrick Taylor on use of the GBT for planetary radar studies. Thanks, and see you then.
Bye now.